The first commercial GTO solvers appeared on the market in 2015, and for the last decade, Nash equilibrium has reigned supreme as the gold standard of optimal poker strategy. Today, we challenge that paradigm, introducing Quantal Response Equilibrium, a groundbreaking new approach for solving optimal poker. QRE represents the next evolution of GTO solving, and will soon become the state of the art. Let me show you why. This is the Nash equilibrium strategy for a 30 big blind heads-up pot. Everything is optimized and finely balanced like the gears of a Swiss watch. But what happens when your opponent takes that Swiss watch and smashes it into the ground? What happens when they take a move that has a 0% frequency, representing no hands whatsoever? This is what happens. A ghost line. This is the fundamental problem with Nash equilibrium solvers, is that they have very poor responses to nodes that aren't supposed to happen. So what's going on here? Why is the solver calling 10-6 and folding ace-9? What is this ridiculous strategy? Well, what you're looking at is essentially a node in the game tree that has not converged. The solver has not finished solving the strategy here. You see, very early on in the solving process, small blind figured out, hey, I never have to shove here. And as soon as that happened, big blind stopped improving their response to the shove. What we're left with is this barely converged strategy. Now here's the issue. In reality, your opponents will take non-GTO lines. In reality, your opponents might just open shove here. And it would be nice if we had a good strategy against that without having to node lock or force small blind to take some strategy, without assuming what their range ought to look like. That is the problem that Quantal Response Equilibrium solves. Now I'll solve this spot using GTO Wizard AI, which uses Quantal Response automatically. You'll note that anytime you're doing any sort of custom solving from now on, it's going to use QRE, whereas the default solutions, the pre-solved spots, will continue to use Nash. So I'll load up the Quantal Response Equilibrium, and the first thing you'll notice is that it looks basically the same in spots that are common, in regular spots. Where QRE differs from Nash are in the uncommon spots, in the ghost lines. So when small blind shoves here, instead of getting noise, we get a nicely converged solution where every hand that calls is a plus EV call. In addition, if I click the Ranges tab, I can actually see what small blind's range ought to look like. Apparently, it's a lot of vulnerable pocket pairs, strong ace-X, and some trash with half-decent blockers. Kind of what you might expect their range to look like in this spot. Now, I didn't tell small blind that it should use this range. Where did this come from? Right? I didn't node lock this. I didn't force it to bet. It came up with this on its own. So how does QRE determine what range to use in these ghost nodes? And what else is new in this update that affects you as a poker player? Stick around to find out. Nash equilibrium is ubiquitous with game theory optimal poker. Every professional player in the world knows what Nash equilibrium is. So they're probably going to be confused as to why we're moving away from such a well-established principle. But I think by the end of this video, you will not only agree with us, but you will welcome Quantal Response Equilibrium as the next iteration of GTO strategies. In this video, I'm going to cover an introduction to QRE. We'll cover its key benefits to you as a poker player. We'll do some strategy comparisons before with Nash, after with QRE. We'll cover the benchmarks and just measure how well it performs. And lastly, for the nerds in the audience, I'll go through a technical explanation about how QRE works on the back end. Okay, let's get into it. So what spots does this affect? Well, going forward, any spot you solve with GTO Wizard AI, that is to say any custom solution, now uses Quantal Response Equilibrium. Any pre-solved solutions, that means spots solved as part of our pre-existing library of solutions, still use Nash. So those were solved before, those haven't changed. Now, if you want to custom solve a spot in GTO Wizard, you need an elite subscription. However, you can still try QRE for free by solving Queen of Spades, 10 of Spades, 7 of Hearts. This is the free flop we give out to people who would like to try before they buy. One of the key shortcomings with Nash equilibrium is how it handles ghost lines. You see, a Nash strategy assumes that players never make mistakes. It assumes people are perfectly rational and no one's ever going to take a non-GTO action. And so as a result, it only optimizes your strategy in spots that are quote unquote supposed to happen in GTO. But what about non-GTO spots? What happens when your opponent takes some ghost line, some 0% frequency line? Well, your strategy facing those ghost lines is suboptimal because they never happen in GTO and therefore it has not converged in the solver. The problem here is a lack of a defined range. If a player takes some action that represents nothing, what's the best response against their nothing range? How do you fight a ghost? Well, that's what Quantal Response Equilibrium seeks to solve. QRE intentionally introduces mistakes into the solution at a low frequency, and this allows it to optimize the strategy everywhere, even in lines that aren't supposed to happen. And to be clear, it gives the same output as Nash in normal spots, but it gives a significantly better output against these ghost lines. What do you mean it makes mistakes? All right, so let me be clear, because when we published this, people were a little confused about what we meant by this. When I say it makes mistakes, I'm saying it is intentionally taking a minus EV action, a fraction of a fraction of a fraction of a percent. We're talking very, very small amounts here, so much so that they are essentially negligible when it comes to the accuracy of your strategy. Now, the way we introduce mistakes is really cool. You see, it's done rationally in such a way that the larger the EV loss, the less likely the mistake is to happen. So mistakes that lose a lot of EV barely ever happen, and mistakes that lose less EV are more likely to happen. And the result of this is that you can actually go and see what the range would look like, and they kind of align with your intuition about like what you think their range might look like in this spot. Now, to be clear, the goal of QRE is not to model some donkey behavior. The goal is to create a highly accurate strategy that is as good as Nash equilibrium, by introducing the minimum amount of mistakes, so the minimum perturbation needed in order to get good responses against ghost lines. Some of you will be asking about how accurate the strategy is. Well, we've benched this, and I'll get more into the benchmarks later, but the exploitability is about 0.1% of the pot on average per street. So it's pretty darn accurate. To be clear, guys, we did not invent QRE. Quantal Response Equilibrium was first published about in 1995, and since then, it's been used in a wide array of fields like economics, political science, and behavioral analysis. QRE is essentially just a better model of human behavior because, well, let's face it, we're somewhat irrational creatures, aren't we? What is new is applying QRE to poker. GTO Wizard AI is the very first poker solver to employ Quantal Response Equilibrium. Let's get down to brass tacks. How does this help me as a poker player? And there are a number of key benefits. So because Quantal Response Equilibrium handles these ghost lines better, it's going to capture more EV against real-world mistakes without node locking. To be clear, you can node lock, but you don't need to. All of that is kind of captured within the rationality premise of QRE. And because of this feature, it's going to outperform Nash equilibrium against imperfect opponents. Imperfect opponents sometimes take non-GTO lines, and, well, frankly, all of your opponents are at least a little bit imperfect, so that leads to better real-world results. Another cool benefit is that you can see what rational mistakes look like and learn how to punish them. And I'll show you guys how to do that in just a minute here. It also leads to a better training experience. In a regular GTO solver, if you take some line that's not supposed to happen, the solver just has no idea what to do. It looks at you and says, how did you get here with ace queen, man? It's not a line. I don't know what to do. Quantal Response, on the other hand, knows what to do. It has some well-defined strategy, even in these ghost lines. QRE also tends to lead to faster solve times on large, complicated game trees. So if you're the type of person that likes to solve with a bunch of different bet sizes at the same time, QRE is going to be for you. In general, we've improved our neural network architecture to lead to sharper, less exploitable strategies on earlier streets. So it's about 25% less exploitable, and we'll cover that in our benchmarks. Lastly, the actual motivation behind QRE is that it has this special quality of being like perturbation stable. So you can kind of poke at the equilibrium and it's still going to be stable even in wildly complicated like multi-way spots where there's many different equilibriums. To be honest, guys, I might be butchering this last explanation a bit because I don't understand it. I'm not an engineer, but suffice it to say, our geniuses in the engine team seem very excited about the use cases of QRE, and it seems to be a crucial ingredient for a bunch of like really cool upgrades we want to do in the future. So QRE is going to act as kind of a crucial ingredient for multi-way solving and for a bunch of other stuff we want to add. So hang in there because 2025 is going to be a really exciting year. Let me give you a real-world example. 7 months ago, somebody posted this to the r/poker theory subreddit. Can't get GTO Wizard to give me an answer. Villain limped called a 4x raise heads up. They called a 70% bet. Then versus my check, he rips it in. I can't remotely figure out what to do in these spots, and GTO Wizard AI refuses to balance a realistic range. So he's sitting here with King Jack facing this 4x overbet on a flush completing turn thinking, well, what the hell am I supposed to do here? And in the past, there just wasn't a good solution to this because either you have to node lock the opponent's strategy, like you have to assume what they're shoving here, or you have to just go into some ghost line. And to this user, remember I replied, this was before Quantal Response came out. I said, yeah, this is going to be a problem with any solver, to be honest. The issue is the turn jam just does not happen in GTO, and even if it's the only size available, the solver would rather just check in the spot rather than go in 4x the pot. So essentially, this means that the strategy facing the shove doesn't converge, since this line is discarded so early in the solving process. The class of game theory that deals with this is called trembling hand equilibria, and it's not a thing with modern solvers. Here are some workarounds. So I tried to give it the best answer that I could give, knowing the limitations of the software at the time. But now we actually have a proper solution to this. So let me first show you what the Nash response looks like to this shove. Here we have a heads up spot. I'll walk you through the line. So villain in the small blind calls. We raise 4x, and they call. Flop is king, jack, deuce. Okay. Now here, they bet 75%. This is a spot where the solver will mix between overbets and small bets, mostly leaning towards small bets, but okay. 75 is not the most commonly used size here, but whatever. We bet this size. They call. Turn is the 7 of spades, completing the spade draw. Here, they're holding king jack, they check, and villain just rips it all in, 450% pot. It may come as a surprise to you that betting 450% of the pot is not an ideal strategy in this spot. In fact, when they shove here, they have no hands, so selected line is rarely used in GTO, solution may be inaccurate. We get this error, right? And if we go into what our opponent's range looks like, we can see it is nothing. So what is the best response against a nothing range? Well, what we end up with is a strategy that's not very well converged. First of all, if I go look at the equity, it says everything is 50%. It's like the old saying goes, it's at 50-50. Either he has it or he doesn't. What are you going to do? This is just an error based on the fact that small blind has no range in this spot. Furthermore, it's just not a very good strategy. We're folding some flushes. Okay, that's a little odd. And then if we go look at the two pair, you'd think if you have, let's say, the jack of spades, you should call a little bit more often than, let's say, jack deuce. Maybe if you have, let's say, top pair and you have the ace of spades, you would think this hand should pure call, right? Or at least call more than the other top pair hands. But again, this spot just hasn't converged because small blind shouldn't be shoving here at all. Okay, so this is the Nash response, and it's not very good. Now let's go over to the Quantal response. And here again, they should not be shoving, right? They just shouldn't shove at all. This one is actually a much better strategy. First of all, we're not folding a flush facing this size, right? And then if we take a look and compare, let's say, two pair, we can see things like if you have the jack of spades, you should call more than without. And if we go over to let's say top pair, you can see that ace king with the ace of spades should call more than ace king without the ace of spades. Right? So really obvious kind of this is the first thing you would think of solutions to this spot. We can also see that there's equity and expected value. And so everything is nicely converged in this spot. Despite the fact that small blind should not be shoving here, we still get a nice response to it. And we can go and look at what their perceived range ought to look like. So if I click ranges here, we can actually see, okay, what are they supposed to be shoving here? If they were to shove, even though shoving is bad, even though this is a bad strategy, if they were to do it, how should they do it? And this is what it came up with. So on the right-hand side, we can see it's shoving with bottom set, pocket twos, which is kind of an interesting one because okay, you're going to get called by a lot of flushes, but you have outs against those flushes that call you. Pocket threes, which is just a bluff. And then if we go into here, we can see 30% flushes, 16% sets, and then for bluffs, we've got stuff like Queen 9 with a spade, so this is a combo draw, and then like a whole lot of flushes at the top. So we've got kind of like a realistic strategy that they're shoving with, right? And this is kind of the benefit of QRE. It's not just that we get good responses against ghost lines, it's that we can kind of see what the mistaken strategy ought to be. Next, I'd like to show you what happens in a trainer. So here's a hand that was played horribly, right? And you can see that in this spot, the Nash equilibrium strategy is question mark. It has no idea what to do. The answer is not available because, well, small blind is never supposed to arrive at this spot with ace queen. Now, in the exact same spot, in Quantal Response Equilibrium, even though it's not really supposed to get you like this, there is a well-converged correct answer. It is just supposed to ship it, right? Even though you can see, like, it never takes this. So on the side, we can see that 25% equals 0% of the time. We're never supposed to take this action. There's still a well-converged strategy for it. Let's talk benchmarks. So I've shown you the strategy comparisons. I've explained to you what QRE is, but realistically, we just need to measure how good it is, right? We just need to put it under the microscope and get some numbers. And the numbers were good. So we're looking at a 25% more accurate strategy, by which I mean it is 25% less exploitable on the flop compared to our last algorithm. It is 3 times faster in big, complicated pots, and it is 38 times better if you consider a metric that uses equal weighted decisions. And I'll get to that in just a second here. We'll start with the flop exploitability. This is kind of our standard method for benching our solver. And you can see different iterations of our solver over the last couple of years, 2023, 24, 25. It's been getting better and better. And our latest iteration is a pretty big step up. So right now, it solves to an accuracy of about 0.12% of the pot, give or take 0.06%. So it's really good. And again, to be clear, this isn't an inherent advantage of Quantal Response Equilibrium. It's just thanks to upgrades to our architecture in general. But to anyone who's worried that introducing, a tiny amount of mistakes into the strategy will make it too exploitable, here I'm hoping I can convince you that that is not the case. It is an extremely accurate algorithm. Another way to bench how good the solver is to figure out how quickly it solves different spots. And so we solved a bunch of different spots, and we measured the average solving time in seconds as well as the maximum solving time. Now, Nash equilibrium is actually a hair faster, so it is 40 milliseconds faster on average. But the human mind is barely capable of recognizing a 40 millisecond delay. What actually matters is the max solving time in practice, right? And QRE is up to 3 times faster on the max solving time. So here you can see this graph. That's the blue line representing the Nash distance, and then the max solving time on the y-axis. And we solve our rivers to 0.1% accuracy. That's why the line stops there. But in general, QRE tends to have a much lower max than Nash. So what this means to you is that you can expect much faster solutions for big, complicated spots. Let's talk about measuring performance in ghost lines. Normally, if you want to measure how good a strategy is, again, you just take the Nash distance, the exploitability. Sometimes we call this the accuracy. It's just a way of asking, if you were to max exploit this strategy, how much money could you win against it? Now, the problem with this particular metric is that Nash distance ignores performance in low or no frequency lines. After all, if a spot is never supposed to happen, then it has no impact on the performance of your strategy. But in practice, people are imperfect and they do take these non-GTO lines. So in practice, these lines do have a direct effect on your EV. Therefore, it would be very nice if we could measure the performance including these non-GTO lines. So we've come up with a new metric, which the team is calling a tree payoff weighted loss, or TPWL for short. We've put out an explanation in the patch notes that goes over this in detail, but in short, TPWL is just the average EV loss if every decision were equally valuable. So regardless of how often you make that decision, how often you get there with that hand, how often that node occurs, how big or small the pot is, like we normalize by the size of the pot. Take away all of that and just treat every single decision as equally valuable, and then average the EV loss of all of those decisions. And what you end up with is a metric that measures every node in the game tree. And what we found is that Quantal Response Equilibrium is far more accurate on this bench. So typically Nash equilibrium will converge to something like, I don't know, 0.4% EV loss, whereas QRE was closer to 0, about 38 times more accurate according to this. So pretty darn good. Now, that said, all this is really measuring is it's answering the question, how good is the quality of the strategy at each individual node in the game tree of all possible decisions? Of course, in reality, the exploitability of your strategy is still a far more important metric. However, having low exploitability does not guarantee good performance in all nodes. And if two strategies have equal Nash distance and one of them has a better tree payoff weighted loss, that will outperform in the real world where people make mistakes. Okay, let's get into the technical explanation. For the nerds remaining, I'm going to explain how it works under the hood. The first point I'd like to make is that there are multiple paths to achieve perfection. You see, we often talk about GTO as if it's this singular, unexploitable strategy, when the truth is that there are a bunch of strategies that satisfy even very stringent accuracy requirements. So in practice, we solve to some Nash distance, let's say 0.1% of the pot. That's an extremely good accuracy. But even that tiny little bit of wiggle room means that there's many possible strategies that will fit inside this circle. And so what that means is that both a classic Nash solver, as well as our new Quantal Equilibrium solver, land in this territory of nearly unexploitable strategies. And this isn't even a new concept. Like, I actually covered this in a video that's 3 years old now, Efficient Studying. And there I demonstrate that when we took 3 classic solvers, so not AI, but like classic old school solvers, and solve the exact same spot with the same bet sizes, what ends up happening is that we get 3 completely different strategies, and yet all 3 strategies had the exact same exploitability, exact same accuracy. So there's more than one path to perfection, guys. Okay, now that we understand that, let's take a look under the hood of QRE. So unlike Nash equilibrium, which is perfectly rational, QRE has some kind of irrationality to it. So we know it makes mistakes sometimes, and the way we define that is through some constant we call lambda. This is the irrationality constant, and the higher lambda, the more irrational it's going to be. So the probability of making a mistake is chosen with a softmax function that uses lambda as an input. Now, again, Nash is a perfectly rational strategy, so with classic Nash equilibrium, it is equivalent to here just using an irrationality of 0, right? So you are perfectly rational, you never make mistakes. With QRE, it does make mistakes. So generally when we're solving, we start with like a higher value for lambda, and then we slowly anneal down to make fewer and fewer mistakes. To be clear, you don't really need to do that per se, it just makes it converge a lot faster, but the point is that we start with mistakes and then we end with a strategy that is nearly mistake-free, but while it was solving, it remembers all those mistakes along the way and it knows how to respond to them. Okay, so in order to help you guys understand this, I've built this interactive calculator, and this is going to show you how QRE will actually pick an action probabilistically. So let's say that you're choosing between checking and betting, and you can check behind and just always lose. Let's say you have some like give up hand on the river, or you can bluff, and maybe bluffing is worth 5% of the pot, so your opponent's overfolding a little bit. Now, here we can see that red, bet, that would be to bluff, is the preferred strategy, obviously, right? And in a Nash equilibrium solver, it's just always going to bluff 100% of the time, right? And this is simply because, well, it's the higher EV strategy, but with QRE, we actually value some mistakes. So we want some small amount of mistakes to go in there. And so what we end up seeing is that sometimes it does check. And how often it checks depends on our irrationality parameter, lambda. Now, at the extreme end, let's say we are extremely irrational, it's just going to do random stuff, right? Like there's no rhyme or reason. It's just going to button click. But as we zoom in, let's say like a 0.1 or something, it's going to make mistakes less and less and less often. Now, in practice, we're starting very, very low. Like again, you don't need much irrationality in order for this to work. So in practice, we're only introducing mistakes at a very low frequency, and it gets slower and lower as we solve. But again, the solver remembers how to play against those mistakes. So even though these are slowly cooked out or baked out of the solution as we solve, the memory of how to play against them remains. On the right-hand side here, we've got some equations. This is just basically describing the softmax function that tells you how it's picking actions. And I've also made a Desmos chart here if you like sliders. Personally, I like the stacked area charts that describe a strategy, but if you guys want, you can like play around with this and see how it changes. I thought this kind of like helped me understand what was going on with QRE. Okay, so you might also ask yourself how it works when there's more than two actions. So I've also built this one facing a bet. And so in this case, we have three choices. We can either fold, call, or raise. And right now I have it set at 0, 0, 0. So we're just going to take all actions equally. So it's perfectly split for now. But let's say that raising is somehow profitable and calling is unprofitable. All right. So in this case, again, at the extreme, always going to raise because it's the most profitable action, right? And that's where we end up. But an irrational player will sometimes, at some frequency, they're going to call. And at some frequency, they're going to fold. And as we solve, we bake out all of these imperfections, but the solver remembers these mistakes along the way. These are the formulas that kind of describe how QRE selects some action. And I've also got a Desmos graph for this one. But look, guys, there's way more that goes into this. Like this is just kind of a small part of solving. There's a whole bunch more that goes well beyond my expertise and more that I can explain here. But I still found it helpful to kind of get a feeling for how QRE works, how the mistake probabilities work and all that. So if you're like a spreadsheet nerd like me, I thought you might appreciate this. Quantal Response Equilibrium is the natural evolution of GTO strategies. While Nash perfects normal lines, QRE optimizes every decision, including spots that aren't supposed to happen. To put it simply, this algorithm outperforms Nash against opponents who make mistakes, which is, by the way, all of your opponents. This upgrade isn't just about better responses to ghostlines, though. QRE is a crucial step towards solving more complicated spots like multi-way and several other projects that our engine team is working on. So stay tuned, guys. There is so much more to come.